to question 5. All right, so in this example, we have find the derivative of each function using the first principles definitions. This is actually coming from a test, from a calculus test, chapter number 1, kind of on limits, continuity, and first principles definition of derivatives. Now, within here, so we have 1, 2, 3, 4, 5. Okay, so 5 different examples. This is going to take us a while. So sit back, okay? Let's take a look, especially since we're using first principles definition. So how would we tackle these? So here's my, my first example. So let me just rewrite it. I want to do it by first principles. So what will I have? So this is going to be the limit as h is approaching to 0 of my function. So if you recall, so this is going to be fx plus h minus f at h, at x, and divided by h, right? So that's the definition of the actual derivative by first principles. So we're finding really just the tangent, so the slope, okay, at all the different points. Now, the first thing before you begin this, when you're doing first principles or any kind of derivatives, I don't know how strict your teachers will be, but you may want to say that this only applies where obviously the function is defined. So right away, because of this denominator, I know that x cannot be equal to 1 here, because if it is, then my function is not defined at all. So that means it's not going to have, so this limit, okay, is not going to exist there. So that's the first thing that you can probably say. Okay, so within here you can literally write out this is only true for x, okay, in R, but x cannot be equal to 1. So this is worth your time in terms of writing it somewhere. Now once you do that, you can go ahead and proceed. So now substituting all of this in, this is not going to be fun, but okay, let's take a look what we get. So if we substitute, we're going to get 3x plus h all over. This is going to be x plus h minus 1 minus 3x all over x minus 1. And then this is going to be all over h. Okay. Now, for the time being, of course, if you're writing this out, I'm going to just concentrate on the numerator. All right. So let me just get rid of this. I want to just simplify this as much as possible. So I'm going to find common denominator between these two. Okay, so if I do that, this is going to be 3x plus h, so that's this numerator, multiplied by x minus 1, minus, so 3x, that's this numerator, and then multiplied by that, so that's going to be x plus h, I guess, minus 1, right there. My denominator in here, so for this whole thing, now becomes x plus h minus 1, and then x minus 1, so that's what I have in there. So now I have to work out with this whole thing, see what it gives me. So if I simplify this whole thing out, what do I get there? So this times this, so it's going to be x squared. So let me do this in fast forward fashion for you. So I'll just simplify the whole numerator. All right, so now what I'm going to do, okay, I'm going to just, so 3x, this cancels out with this. This cancels out with that. And that only leaves me. So notice all of them have an h. I'll take that h out. And all of them have a 3. So I'm going to take 3h out of there. So that's going to be now just x minus 1. And this one is negative. Oh, I took that out. So that's going to be just minus x. So actually this cancels as well. So this is going to be just negative 3h. And then in the denominator, so I have all of this junk. So duplicate, bring it back down. And don't forget, we were dividing. we're dividing by h. So if we're dividing by h in here, so now this h and this h cancels, and there you go. And now as the limit h is approaching to 0, I'll have -3 all over. Okay, so this h is gone, goes to 0. So this is going to be x minus 1 squared. So that would have been our derivative. And again, this is for x not equal to 1, right? So we cannot have that. But for the rest, this is what we would have. All right, so now let's find the derivative for this one. This one's a little bit nicer. We don't have any restrictions. So this is, t. This function is defined everywhere because it's just a polynomial. So in this case, just a quadratic, to be honest with you. So how would we do this? Okay, from first principles. So this is going to be limit. This is, I guess, as h is approaching to 0, but this is of t. So now substituting in here, okay, so based on first principles, so we got to take t plus h. So -16t plus h squared plus 12t plus h. So that's this one. Minus, right, our actual, so here, the -16t squared plus 12t. And this is all over h. Now we're going to have to be massaging this out and trying to see what cancels and what doesn't cancel. Okay, so let's do that. So I'm going to work on this square. So we get, this is what we have. Now, just kind of expand this whole thing out. So now I got to bring this inside of the bracket. So -16t squared right here. -32th. So that's right there. -16h squared. And then all of this junk right here, which we can put in right there. Now, to cancel, so notice this is going to cancel with that. So that's gone. Anything else that cancels, so that's going to be, I guess this 12t cancels with this -12t, so that's all I have left there. So this is plus 12h, that's the only thing remaining, okay, over there. And then all of this divided by h. So of course, from the numerator, the h can come out. So this is -32t minus 16, I guess, h plus 12. And then all over h. So that h cancels off. And now as we take the limit, h is approaching to 0. So this is approaching to 0. So our derivative becomes -32t plus 12. And this is for t, okay, defined for all. We didn't have any restrictions, so there we have it. That would be the derivative for this one based on first principles. So that's pretty neat, okay? So that's another example. Here's another example. This is for absolute value. This one is not fun to do whenever there's absolutes. I do hope that you kind of remember the absolute value function. So if you sketch this out, because I'm just looking at this because I know that dealing with absolutes, we're not going to have this function, the derivative defined, okay, at a particular point. In this case, at 2, because we're thinking back of the absolute value, so the absolute value function looks like this, right? This is just x. Now this is being transformed. It's transformed up, okay, and then here to the right. So really this one, if you remember your transformations, okay, on absolute values, if you don't, actually I'll put up a link up above there because I think specifically just for the absolute value. So you can look at that to refresh your mind. So this is going to be 1, 2, and then it's going to shift up 1. So we're basically, so this function looks like this. Okay, that's how it's going to look like. And this point is 2, 1. Right, that's what we have. And then so the slope over here on this side is -1, and then the slope on this side is going to be +1. So we can break this up nicely into 2. Okay, so that way we don't have to deal with the absolute function, which really helps us in terms of finding the derivatives over here, because the derivative is nothing else, if you remember, just the actual slope, right? What is the instantaneous rate of change at a particular point? So at this point, it does not exist. So at 2, we certainly will not have a derivative, because there's an abrupt change. So the limit from the left-hand side will not equal the limit from the right-hand side. So not continuity. This is with regards to the slope. So you can see that the slopes are different because these are just lines. And now what makes this very nice, and now actually I don't have to do a lot of work in here. So, you know, what I can say is, so this is the limit as h is approaching to 0. And now I'm going to assume that this is for x less than 2. So for x less than 2, this function, okay, so what I have in here, so this is going to be, so this is, sorry, 1. So this is going to be 1, this is 2, this is 3. So this function right here basically is -x plus 3. Okay, so that's that function right there. So the slope is negative, and it will have a y-intercept of 3 above there. Okay, so that's what you're going to run into there. So now that's not very difficult, right, to find the limit of that function right there. So we would have to do, let me erase this and make this more meaningful, because the way that it's written doesn't make sense here. So we have that. Now I have to take this function, so we would substitute, so negative, this is x plus h plus 3 minus, you know, -x plus 3 all over h. And if you do this, of course, you're going to get -1. Okay, so because that's going to be the slope. This is for x less than 2. And now for this, well, this is the slope is 1. Okay, and then if you would carry it through, okay, so you'll notice this would have dropped to 0, and this is to 1, so -1. So your other one is x minus 1. That's your second one. This is for x greater than 2. And this will have a slope of 1. Okay, so -1 over here, and then the +1 over here. And you can certainly break this down, and I would recommend it whenever you do have absolute values. Because if you are trying to deal with absolute values all at once, and then doing it by the first principles, always break it down. You know, find where that vertex is for it, where that abrupt change is, and then do to the left. So this is what you would do here. So if you had a teacher, you would show them this. You would tell them that you're breaking it down. So you broke it down into the left. And then when you're breaking it down to the right, you would take this one and you'd find the equation of that line. You know the slope, you know the point, so you can find the equation of the line, right, of this one. I just extrapolated because I knew the slope was 1 and the other one was -1. And then you would do two things. You would do it, so this one is the yellow one. That's the work that you would show for the yellow one. Right here, you would simplify it, you would get this. And then for the green one, for that one, you know, you would basically say that you were trying to find the limit as h is approaching to 0, and then you would have, this is of the function x minus 1. So now if you substitute it in, so this would be x plus h minus 1 minus, okay, so that's your functions, and then minus x minus 1 all over h. And now you can just simplify. Simplifying this one is easy. It's not a problem at all, okay, that you're going to be running into, and then you'll just get your answer of 1. That's how you would show your teachers, okay? So absolute values I always was freaking out when I was a student because I'm like, how am I going to deal with this? You know, like, especially in first principles, or even not first principles, just finding derivatives. But don't forget what the absolute value actually is. And if you understand your transformations, you know, this is where it's handy, that grade 11 stuff. Then, you know, you can make it very visual and it will make sense to you. So that's another example. I hope you found that one useful. Okay, so here's another one. This one's going to be a little bit of work. So we're finding the derivative here, except we're finding the derivative from first principles. And if you were using first principles, you know, we got to be careful. So the first thing, again, like all your cases, just make sure that you know where this function is defined. So clearly t cannot be equal to 0 right here because we would get a 0 in the denominator. And then also, you know, we need, under the radical, that 9 plus t, we need this to be greater or equal to 0 there. Otherwise, you know, that radical is not defined. So this just simply tells us that t has to be greater or equal to, I guess, negative 9 over here. So that's what we need. So our domain right here is t. It's all of r, such that t is greater or equal to negative 9, but t cannot be equal to 0. Okay, so we run into a problem there. All right. So now with that, okay, stated, you can state that for your teachers. Now we need to plug all of this thing in. So first principle, so limit as h is approaching to 0, okay, of our function, but we're substituting t plus h, right, into this function. So that is going to be 9 plus, this is t plus h, minus the 3 all over t plus h minus, I'm going to be running out of space, I'll bring it down. So minus, this is going to be square root of 9 plus t minus 3 all over t. So that's what I have there. Yep, 9 plus t, okay. And then this whole thing over h. So we're going to have to do a lot of massaging in here to try to figure out what we're going to get. Okay, so forget the denominator. So this h at the moment. Okay, we'll forget about that. But we are going to find a common denominator between these two. And that's going to now give us this. Okay, so t multiplied by all of this. All right, so duplicate of that. Minus, now the other one is going to be t plus h multiplied by all of this right here. Duplicate, bring it down. Okay, so far so good. And then this, of course, is all over t and t plus h, and then this h right here. So we have that. So that's not bad. All right, so now, okay, if I bring this inside of here, massage this out. 9 plus t plus h minus 3t minus, all right, so now this t distributes across, it's going to be t 9 plus t minus 3t, then take this h, distribute that through, so plus h 9 plus t, and then minus 3h. That's a lot of junk. Okay, so all of this, okay, divided by all of that. We'll worry about that after we simplify. I'm sure something cancels here. Now, this sign, if I bring it in here, so obviously it will change all of these signs. Okay, so all of that will be updated. So let me duplicate, bring it down. I'm just going to concentrate on this. Okay, so that means this is going to be negative. This one is going to turn positive. This one's going to turn negative, and the last one is going to turn positive. So I have that. All right. So this is what we have in here. Can now shift these things out. Okay, does anything cancel? Let's hope this one is gone. 3t that. Yeah, unfortunately, I don't think anything else does. At least not for now. All right. Okay, so let's see what happens in here. Okay, so now I'm going to change colors. Okay, so because I still can't forget about this. So what I have now, I'm going to have this. I'm going to group these two things together, right? Because they look kind of alike. So I have the T, and then I have 9 plus T plus H, right? Minus. This is going to be minus the 9 plus T all over H, T plus H. So notice this T and this T cancels. So that's gone. Now, does that help us any? Okay, because so this is still going to be a problem within here. So that doesn't help us as much. Okay, the other one, this one is the other. Okay, so these last two, so these ones. Notice what we will have. So over there, we're going to have negative H, 9 plus T plus 3H. So this one's nicer because that H, this is T plus H. So this H will cancel out those H's. So this is just going to be negative 9 plus T plus 3 all over now T and T plus H. So now we don't have a problem here because we can let H go to 0, and we will get, okay, what the derivative is here as H is approaching to 0. So that one is pretty good. Oh, okay, so now we can use our little trick, okay, because it's going to be indeterminate. So notice, okay, I do have a subtraction here. Okay, so I fell into my own trap. So now, okay, this is what I'm going to do. I'm going to take, okay, so this is difference of squares. So 9 plus T plus H minus 9 plus T, right? So if I'm working out on this, okay, so that denominator, so what I'm going to do is I'm going to multiply both sides by 9 plus T plus H plus 9 plus T, right? So I'm going to do that to both numerator and denominator. So I'm using one of those tricks in here. Okay, so this is still H, T plus H. Okay, so now this is going to be 9 plus T plus H minus 9 plus T. So that's all of this multiplied. So that's the difference of squares. Beautiful, because now I have 9 minus 9, T minus T. Okay, perfect, which now leaves me just H. So I have H on top divided by H. T plus H, and now all of this junk right here, which indeed is, it's not great. Okay, however, that's not going to cause us any issues because it's a plus. So that's that. So that means H and H cancel, so that's going to be 1 all over. Okay, let me just make sure this is that. That's what I will get in here. Okay. And now as I let h tend towards 0, so if I would do that, so that means this is going to just tend towards t. This is going to tend towards 9 plus t plus 9 plus t, which is really 2, right? 2 of them. So 2, 9 plus t. So that's what I will have right there. Okay, and so that is my derivative. And then, I can't forget still this. Okay, so let me copy this. If I bring it down, paste. Okay, now if I let h tend towards 0 here, that h tends towards 0, so this is going to be, I guess this is like 3 minus 9 plus t. I can just swap those. I like that negative in front, and this is going to be t squared. Okay, so plus that, and then 1 all over 2t 9 plus t. Wow, that is super ugly. But that is the derivative. All right. So that's a very hard question. We had to catch this. I had to catch myself here because I wasn't sure what to do over here. But I guess indeed I can just multiply by the difference of squares. This one was not bad. If I grouped those two things together, that worked out very nicely. So that's what I would have had over here. Now you can massage it, do whatever you like to this. And then don't forget that it is being restricted, right? So these are restrictions within here on the actual domain of this one. All right, okay. So that's another one for us. Here's another example for finding the derivative with regards to kind of first principles definition of this particular function. Okay, so first thing again, always ensure, so y cannot be equal to 0 because this function is not defined there. Now finding it from first principles, so if we substitute y plus h in here, right? Okay, so our first principle, so limit as h is approaching to 0, substitute that in. I'm going to just for, I guess, convenience in here, so this will be just substituted right away. So I'll put y plus h cubed minus 1 over 3 cubed. This is all over h. That's what we would have. And now we have to massage this out to figure out what answer we would get. All right, so within here, as we are approaching this, this is going to be, so I guess let's find the common denominator. So that's this, y plus h cubed all over, it's going to be h and y cubed, and then y cubed, y plus h cubed, so that's that. So as the limit h is approaching to 0, okay, so this is what we'll have. Now this is going to be annoying, because I have all of this junk. So let me just do the expansion. I'll use binomial expansion actually. I'll use that because it's cubed. So we will have y cubed minus, and then this is going to be y cubed. Right, so plus 3y squared h plus 3y h squared, and then plus h cubed. So I'm just using the binomial expansion here. Okay, you can expand it out throughout as you like. Now the denominator, okay, I'm not going to worry about it, but for the time being, I'll actually notice that this will cancel this off. So all I'm going to have is negative 3y squared h minus 3y h squared, and then minus h cubed divided by all of this junk right here. So duplicate it. Okay, so now this h, notice, going to cancel. Going to cancel one of these. It's going to cancel one of these. So what we have in here is we're going to have negative 3y squared minus 3yh minus h squared divided by our junk over here, y plus h cubed, y cubed. Now if we let limit of h is approaching to 0, this is gone. It's going to be 0. This is gone. This little h is gone. And so what we get, okay, in here is negative 3y squared all over. So y to the 3, y to the 3, which is y to the 6. So this is just negative 3 all over y. So notice this and this by your exponent rules. This is going to be to the 4. And that's what we would get over here, right? So for this one, that would have been our derivative. And of course, you know, it cannot be equal to 0, but we already said that in the beginning, right? So that was for this. All right. Okay. So that was another example. I hope you found it useful. Okay. We'll see you in a future video. Cheers, everybody. Bye.